Alright, hi and welcome. Today we'll be talking about permutations, combinations, or more specifically the study of combinatorics. In other words, counting items in sets or counting items certain ways. And as you can see, I've got several formulas already on here. Okay, one of the most old-fashioned ways to actually do something is to make a tree diagram of choices. Okay, so if you look at a tree diagram, it's really easy, but it can also get really complex fast. Like for example, if I'm making two choices in the beginning, you will see this a lot in statistics. So this is actually a really interesting thing. Okay, and then I make two choices again. I've already got four possibilities of paths that I could take, and then if I make two choices off of that, okay, it's getting a little bit messy, but you get the idea that there's going to be 8 possible paths I could take. So tree diagram, when all else fails, a tree diagram really helps working with this stuff. Okay. All right. Now, first off, before we get into permutations and combinations, we need to talk about independent and dependent events. Now, independent events are events that the probability of one does not affect the probability of the other. Like, for example, when rolling dice, one dice does not affect the other unless literally they are attached to each other, and then that's a weird dice game and you should not be playing that. Dependent events are where one's probability affects the other or subsequent probabilities just by doing that, and that's usually connotated by events of with or without replacement. With or without replacement. Yep, I did spell it right. Okay, cool. All right, so with replacement, that would be actually a dependent event, and without replacement would be an independent event. All right, now let's take a look first at the base accounting principle. Okay, and it is basically saying one event can be chosen P ways, another event can be chosen Q ways, then the two events can be chosen P times Q ways. And I also have referred to this as the fundamental counting principle. It doesn't matter which one you think it is, it's just as is. Okay. Now, a great way to actually explain this one is when you go to a restaurant and you have choices for meals. So let's say you have 5 appetizers, looks like 5 apps, 4 entrees. Now let's make it more interesting. Let's make it 6. 6, 10 drinks, and 4 desserts. Okay. Now, how many possible meals, how many combinations of meals, how many different types of meals could I have? Okay, so this is where the fundamental counting principle comes into play. So we would do 5 times 6 times 10 times 4. And if we check that out on our calculator, that is a pretty messy number. 5 times 6 times 10 times 4. It should be 1,200 distinct meals. Okay. All right. Now, how does that work? Why does the fundamental counting principle work? Well, if you think about it, we have a certain amount of items here, and then a certain amount of items here, and a certain amount of paths here. Well, actually, going back to the tree diagram, it actually explains it perfectly. Okay, so if you notice earlier, I said that all of these are 8 distinct paths. Well, guess what 2 times 2 times 2 is? 8. Okay, so this one would have 5 paths here. This one would have 6 paths off of each of those 5 paths for a total of 30. Okay, and then we would have 10 paths off of there, so that would be a total of 300. All right, and then 4 more paths on top of those 10 paths, on top of those 6 paths, on top of those 5 paths, you've got 1,200 branch tree diagram. Now, that's why the fundamental counting principle actually came into play, because no one wanted to actually write out that tree diagram. That's ridiculous. I think one time I had a class that we actually calculated the difference between Port of Subs, which is a West Coast chain of submarine sandwiches, and Subway. And we found that even though Port of Subs had a greater amount of meal, or it had, different types of stuff, and actually everyone liked their sandwiches better. Subway had a greater amount of combination, so you could have a greater amount of distinct Subway sandwiches. It was really interesting. Okay, now that covers counting items, okay, that are just pretty much straightforward, that type of stuff, okay? All right, now let's talk about combinations. Now, whenever someone hears combination, they think, oh, combination, and then that's it. But there's actually two types of combination. There's a regular combination, okay, and there's a permutation. So what is the difference? Okay, the difference between the two is that the differences between permutation and combinations are order matters in permutations, okay, and I like to associate the word pick with permutations because you are picking, so you're being choosy, so order does matter. And the orders don't matter in combinations because you are choosing. You're just choosing at random. Not at random, but you're choosing which combinations you want, okay? All right, so there's actually two types of formulas for permutation. So we're going to talk about order matters first. Okay, now if you have an n amount of objects and you're choosing n of them, your actual permutation is going to be n factorial. Now n factorial is just the numbers below multiplied with the number that is. So like for example, the best way to do this is 6 factorial. So that would be 6 times 5 times 4 times 3 times 2 times 1. So you go all the way down to 1 and you just multiply all the way down. So that one's pretty easy. Now, if you are doing a permutation where you have an amount of n objects and r are chosen at a time, it's n factorial over n minus r factorial. Okay, that one's pretty hard to remember and stuff, but if you just think about it, it actually makes a whole lot of sense. Okay. Plus, on Desmos, if you use Desmos, it will actually do these calculations for you, or your graphing calculator. Now, if you're using a graphing calculator, you will need to put your n, whatever n is, and then you find the button in math that's under probability, NPR, and then you put your r, and then you press equals. Okay. Now, if you're doing it on the on Desmos, you're going to put NPR, then parentheses your n, comma, then your r. Okay, and that's how you actually find those calculations. And then same thing with NCR when you're doing combinations. Okay. Now, combinations are going to be n factorial, except it's going to be this little addition right here of this r factorial, and that's the only difference between permutation and combinations. Now, the reason why that is because this will take care of the order that doesn't matter. So in other words, if we're choosing numbers at random between 1 and 10, and we only wanted to choose 3 of them, how many possible combinations could I have? 1, 2, 3 would be the same as 3, 2, 1, so we would divide by r factorial. Okay, whereas if we were picking numbers at random and we cared about their order, how many possible permutations we would have, 1, 2, 3 would be different from 3, 2, 1, so that's why we don't have the r factorial here. Okay, let's actually work on some actual problems. Okay, so in a downhill race, 20 racers are vying, or Ving, or however you want to say that, for the top 8 spots to advance. How many possible finishes could happen? Okay, so what you could do is you could seriously type this out as you go. You want to be able to think about this. Now, if you notice, I left out all possible clues as to how this works. So if we think about it, if, let's say we numbered the racers from 1 to 20, and let's say 1 through 8 finish first. Okay, all right. Now, would that be any different than, let's say, let's reverse that, 8 through 1 finish? Is that any different? No, it's not. Because all we're doing is looking to advance. So we don't care about order, so this would actually be a combination. Okay, so what is n, what is r? N is the amount of items you're choosing from. R is usually the smaller number, which you're actually choosing the amount of. Okay, so on this one, this would be 20, choose 8, okay, which if you're putting into a calculator would be 20 NCR 8 And if you're putting it into Desmos, it's going to be NCR parentheses, or not parentheses, yeah, parentheses, 20, comma 8. Okay? All right? And if we do that real fast, NCR 20, choose 8. Okay, we are going to get 125970. So that is 125,970 distinct finishes. Okay, now let's say that those 8 advance. We want the possible amount of winners podium possibilities. Okay, now usually in that you would have 3 winners: a silver, a bronze, and a gold. Okay, so order does matter in this. So if, once again, we number them 1 through 3, okay, finish first, okay, in that order, 1 gets the gold, 2 gets the silver, and 3 gets the bronze. That is different from 3, 2, 1 finishing first. Okay, so because that's different, this one, the order does matter. So we would actually, and winners, I better put an I in there. I'm going to drive myself nuts. Okay, so this one order doesn't matter. This one order does. Oh dear. Let me get making all kinds of silly mistakes. Okay, so on this one we're definitely going to be doing NPR, so I'm going to do NPR. Now on this one, if you notice, our number has shrunk from 20 to 8, so it's 8 choose, or 8 pick 3. Okay, so when I put it into my calculator, don't forget to put the 3 at the end, because if you do 8 pick 8, you're actually going to get something screwy, and there should be 56 distinct winners podium possibilities. Okay, all right, that is it for working with permutations and combinations.